So, in my previous PO Maths video, we learned how to calculate the gradient of a curve at a given point. As we saw earlier, I took the graph of y equals x squared for an example and found the gradient of the curve y equals x squared at the point A with coordinates 3, 9 is 6. And we also found the gradient of the chord AP connecting point A to point P. So, we learned earlier as point P gets closer to point A, the gradient of the chord AP got closer to the gradient of the tangent to the curve at point A. Now, let's take this graph of y equals fx. So, as I said in my previous PO Maths video, gradients of curves, the gradient of a curve is constantly changing. And hence, the gradient of a curve at a given point is defined as the gradient of the tangent to the curve at that point. So, in the graph y equals fx, I'll take this point, so I'll label this point A. Now, the gradient of the curve y equals fx at the point A is the gradient of the tangent at this point. So, here's the tangent at point A. Now, I'll take this point B, and point A is connected to point B by the chord AB. So, as point B moves closer to point A, the gradient of the chord AB gets closer to the gradient of the tangent to the curve at point A. In order to make this clear, I'll use coordinates for A and B. So let's say the x-coordinate of the point A is x, and since this is the graph of y equals fx, then the y-coordinate of point A is fx. So point A has the coordinates x, fx. And let's say the x-coordinate of point B is x plus h, and since this curve has the equation y equals fx, the y-coordinate of point B is fx plus h. So point B has coordinates x plus h, fx plus h. Now here, h represents a small change in the value of x. Now since we know the coordinates of A and B, in order to find the gradient of the chord AB, we can use the formula m equals y2 minus y1 over x2 minus x1. I've already covered about how to find the gradient of a straight line joining two points in one of my previous PO Maths videos. If you want, check it out for more details. So, the gradient of a straight line joining two points equals the difference in y-coordinates of the 2 points divided by the difference in x-coordinates of the 2 points. Then, the gradient of the chord AB equals fx plus h minus fx over x plus h minus x equals fx plus h minus fx over h. Now, since we know as point B gets closer to point A, the gradient of the chord AB gets closer to the gradient of the tangent to the curve at point A. That being said, as h gets smaller, the gradient of the chord AB gets closer to the gradient of the tangent to the curve at A. This means that the gradient of the curve at A is the limit of this expression as the value of h tends to 0. We can use this to define the gradient function. The gradient function can be used to find the gradient of the curve for any value of x. The gradient function or derivative of the curve y equals fx is written as f dash x or dy over dx. Then, f dash x equals the limit as h tends to 0 of f of x plus h minus f of x over h. So, this means the limit as h tends to 0. Since we cannot evaluate the expression when h equals 0, but as h gets smaller, the expression gets closer to a fixed value or limiting value. Using this rule to find the derivative is called differentiating from first principles. Today, in this video, I am only covering about where differentiation originates. I will be covering about differentiation starting from my next video. Now, let's take a look at a few examples. The point A with coordinates 2, 4 lies on the curve with equation y equals x squared. At the point A, the curve has gradient g. Show that g equals the limit as h tends to 0 of 4 plus h. So, at A, x equals 2 and y equals 4. Now, the gradient function can be used to find the gradient of the curve for any value of x. So, using the definition of the derivative with x equals 2, g equals the limit as h tends to 0 of f of 2 plus h minus f of 2 over h. Now here, the point A is lying on the curve with equation y equals x squared. And here, f dash x equals the limit as h tends to 0 of f of x plus h minus f of x over h is for the curve with the equation y equals fx. Now, in this example, the curve has the equation y equals x squared. So, the function fx equals x squared. And hence, we need to square everything inside the brackets. Then, g equals the limit as h tends to 0 of 2 plus h squared minus 2 squared over h. Equals the limit as h tends to 0 of 2 plus h times 2 plus h minus 2 squared over h. Expand the brackets, then g equals the limit as h tends to 0 of 4 plus 4h plus h squared minus 4 over h equals the limit as h tends to 0 of 4h plus h squared over h. So here I'll factorize the numerator 4h plus h squared. Then g equals the limit as h tends to 0 of h times 4 plus h over h equals the limit as h tends to 0 of 4 plus h. H was a common factor, so taking h out of the brackets and h cancels out from both the numerator and the denominator. So g equals the limit as h tends to 0 of 4 plus h. Now if we were to deduce a value for g, that is the gradient at point A with coordinates 2, 4, then as h approaches 0, the limiting value is 4. So the gradient at point A is 4 and hence g equals 4. Moving on to another example, the point B with coordinates minus 2, minus 8 lies on the curve with the equation y equals x to the power 3. At point B, the curve has gradient g. Show that g equals the limit as h tends to 0 of 12 minus 6h plus h squared and deduce the value of g. So at point B, x equals minus 2 and y equals minus 8. Then using the definition of the derivative with x equals minus 2, g equals the limit as h tends to 0 of f of minus 2 plus h minus f of minus 2 over h. Now here the function is fx equals x cubed, so we need to take the power of 3 for everything inside the bracket. Then g equals the limit as h tends to 0 of minus 2 plus h to the power 3 minus minus 2 to the power 3 over h. So to make it more clear, I'll expand the bracket separately. Remember, I'm just doing it separate to make it easy so I don't have to write the whole function again. Then, minus 2 plus h to the power 3 equals minus 2 plus h times minus 2 plus h times minus 2 plus h equals 4 minus 4h plus h squared times minus 2 plus h equals minus 8 plus 4h plus 8h minus 4h squared minus 2h squared plus h to the power 3. So, I'll collect the like terms. Then, minus 2 plus h to the power 3 equals h to the power 3 minus 6h squared plus 12h minus 8. So, g equals the limit as h tends to 0 of h to the power 3 minus 6h squared plus 12h minus 8 minus times minus 8 over h. As minus 2 to the power 3 equals minus 8, then g equals the limit as h tends to 0 of h to the power 3 minus 6h squared plus 12h minus 8 plus 8 over h equals the limit as h tends to 0 of h to the power 3 minus 6h squared plus 12h over h. Factorize the numerator, then g equals the limit as h tends to 0 of h times h squared minus 6h plus 12 over h. H cancels out, so g equals the limit as h tends to 0 of h squared minus 6h plus 12. Then, rearranging this to get the answer given in the question, g equals the limit as h tends to 0 of 12 minus 6h plus h squared. Now, as h approaches 0, h squared also approaches 0 and minus 6h also approaches 0. Then, we'll have a limiting factor of 12 as h tends to 0. So, g equals 12. And hence, the gradient at point B with coordinates minus 2, minus 8 equals 12. Moving on to another example, prove from the first principles that the derivative of 6x is 6. Here, from first principles means that you have to use the definition of the derivative. Now here, fx equals 6x. So, using the definition of the derivative, f dash x equals the limit as h tends to 0 of 6 times x plus h minus 6x over h. Then, expanding the brackets in the numerator gives us f dash x equals the limit as h tends to 0 of 6x plus 6h minus 6x over h equals the limit as h tends to 0 of 6h over h. H cancels out, so f dash x equals 6. Let's take a look at another example. Prove from first principles that the derivative of 10x squared is 20x. So here, fx equals 10x squared. Then, using the definition of the derivative, f dash x equals the limit as h tends to 0 of 10 times x plus h squared minus 10x squared over h. So first, I'll find the value of x plus h squared. So x plus h squared equals x plus h times x plus h equals x squared plus 2xh plus h squared. Then f dash x equals the limit as h tends to 0 of 10 times x squared plus 2xh plus h squared minus 10x squared over h. Expanding the brackets in the numerator gives us f dash x equals the limit as h tends to 0 of 10x squared plus 20xh plus 10h squared minus 10x squared over h equals the limit as h tends to 0 of 20xh plus 10h squared over h. So, factorize the numerator, then f dash x equals the limit as h tends to 0 of h times 20x plus 10h over h. H cancels out, then f dash x equals the limit as h tends to 0 of 20x plus 10h. Now as h tends to 0, 10h also approaches 0. So as any terms containing h will have a limiting value of 0, the limiting value as h tends to 0 is 20x. Then f dash x equals 20x.